and start recording. Alrighty. Hopefully OBS doesn't shit the bed. Okay, so today we are moving on to colliding things together. So let's say we have a shape. And I think for simplicity we'll start with my notes actually. Okay, so let me just get my tablet working. Okay, so we have a shape like that and another one like that, and they're hurtling towards, actually we'll say that this one, for the time being, we're going to pretend is just fixed in space, and this one is hurtling towards it. And so eventually, after several frames, we're going to end up in a position where these shapes are intersecting. And we have a collision. And so what we want to do when this happens is, so we have collision detection, we can detect when these things are touching. Now we want to do a collision response, which is sort of the other half of this problem. And presumably what we want to do is to have this shape bounce out in the opposite direction. Now, we pretty much have done all of the components of this. We have all the maths we need, and we can detect this collision and interesting information about it. For example, we can determine the axis on which they are colliding. And so if we have our shape like that, a shape like let's say that, we could also say that we have a similar axis on which the collision is taking place, and we have the amount of separation as well. And so what we're going to do first is we're going to sort of do all the maths and all the thinking and designing about how we handle this collision, and then either we'll sleep on it and do the programming in the next session, or if we're really quick about it, we will do the programming as well this session. So this is basically a design session. So normally I'd be handing over to you to start doing some design. You don't have a tablet and stuff plugged in though. So
oh, I do have a tablet, but yeah, I wasn't expecting. It's kind of packed away.
Yeah,
I can get it for the next one.
That's all right. I probably should have said something like so you had time to set up, but that's fine. So I will continue doing the drawing, but it's probably help anyway because it helps to be able to explain these things. So I'm basically going to effectively hand over to you and say, right, how do we handle this collision? And so we might have this other shape that I drew, perhaps it's a box and it's coming in, it's got velocity, it's going to hit at some point, and we'll get the axis of separation, and we want it to bounce off. Where do we start?
Well, I have a sort of pre-start question.
Yeah.
And maybe it's later, but obviously in the sort of the real world, when you bounce a ball against the wall, I mean, maybe it does in quantum things, but it doesn't go into the wall and then come out. It kind of hits the wall, comes out. And I know that when you draw the shape that's over the triangle right now, it's the feedback for the visual, drawing that, you probably will never draw the square inside the triangle because this is just where it is on that tick, and then we're probably going to correct it with that force away before they even ever see it. So yeah, what you're drawing in red there. So I guess my question was, Do we have to? Is there a step where we have to like force correct that first and then apply the force, or is just the I guess no, I don't know if it's magnitude, but like the amount of force is going to like be necessarily high enough that the next tick will not be interpenetrating the other object, or is that just like, or is it just doesn't matter in this world because it's just we're just doing shapes in 2D and it's going to overlap and then it's going to like we'll apply the force after. Is there a discrete step for that or not?
Okay, so there's a few ways of handling that. One way that we can handle that, and this is an aside because we're not doing this way. We might look at this way in the future because it's interesting. So say we have a fixed object here, and we've got an object coming in like a circle, and it's moving this much per frame. And what we will do is, you'll recall our Minkowski stuff from ages and ages ago, and basically what that was is like, we have one shape and we have another shape and we add those together and we end up with like the addition of every vector in this shape. So it's like, this vector and that vector plus every vector in this shape, so this vector and that vector, and you end up with a shape that looks like a rounded rectangle here. We sort of do a similar thing here, and that is if we take this circle and we add just a single vector. So we're doing circle plus one vector equals, and we get a shape that looks like this plus that vector is going to be this. And so rather than doing the collision between the circle and the triangle here, what we would do is we would do the collision between the triangle and this sort of elongated circle that I've drawn.
Right. It
Very
kind of
poorly.
provides like its own buffer based on like that Minkowski distance.
Yeah, so you can imagine that once you calculate the amount of penetration you get here, so let's say that sort of, because it's not the best shape for doing this with, that gives a clearer idea about what's happening. And then we have our fixed triangle. And so now when we do the separation here, here's our axis of separation, we can actually see how far into the shape it penetrated along its motion vector, which is that cyan one. And so what we then do is like, all right, well, we'll do a little bit of maths, and you can imagine this vector maths is a little complicated, but we'll we have this vector here, and we have the motion vector, which is like I sort of roughly draw it like there, and we do whatever we need to truncate it there, basically. And so then we have a new motion vector, and that's going to tell us exactly how far we can move before we hit this surface here. Excuse me. And so that's one way we could handle the collisions that's very robust. Does that make sense?
Yeah, I mean, I couldn't do it, but
I'd have to look it up and do a bit of research myself because I can't remember the details. I believe I'll leave it because I can't remember correctly enough.
but for our purposes, like for this exercise, are we just Or doing something different, I guess.
We are going to do the cheap and nasty way, and that is sort of what you were talking about before. There's two ways we can handle this situation. One is we just ignore it and just be like, well, it'll bounce off, it'll get out of there eventually. The other is we just handle it in two steps. So it's like, all right, well, we've got a box coming in, and on this frame it's going to be here. And so first step is we just separate it out like that, and it's like, oh, look, it's separated out. And on the next step, on the same frame, we then calculate the collision response and send out that way. And this is probably going to be good enough for our purposes.
Although, won't the green vector not be an accurate force if we're basing it off the cyan one because the blue one is already moved? We have to like
yes. So let me try and draw that more accurately. In fact, so
which I have no idea. I don't know what kind of like damping forces you apply to two things with mass that say that you should account for the fact that it penetrated and changed it. So it's not going to be just a pure bounce off, right? It's not going to. The green one isn't going to just be what's the opposite force that I was moving in, or the perpendicular or whatever force that I was moving in when I hit the triangle. It's got to be like that, but also the mass of the two objects, like the collision would, they could go slower, wouldn't it? I don't know. Might be out to lunch here.
Well, let me talk you through that. So I'm just trying to draw this a bit more clearly. So this is the step. Blue, cyan to blue is the step where we do the separation. And then we do collision response. So we've got green, which is going to be, we've got the motion vector coming in this way, and it reflects off this thing.
Yeah.
And we get this motion from the blue shape, so it ends up like here, let's say. Whereas if we were doing it this way, let's see, we'd stop, rather than separating out to blue, we'd stop and end up at red. Then we'd still have some time step left on the motion, so we'd actually move out a little bit in this direction extra, because we've still got to actually calculate that step, and then the rest of the frame. So we'd then move to, I'm going to run out of colors doing this, so we'd then finish off, actually no, I guess that doesn't, because I've calculated like 2 frames here.
Are you saying we have extra time step because we prematurely counted the overlap because of the whatever Minkowski padding? Do we have to wait until the actual penetration? Is that what you mean by extra time?
So we'd end up there, but basically for the cyan and blue one, this is going to be time step 1 is going to take us from here to here and separate us out, and then give us a new velocity vector, and then time step 2, which is in green, is going to move us out here. Whereas in this one, red, our first time step is going to is going to end us in cyan, and it's going to be like, shit, we actually should have stopped earlier, so it's going to stop there. And because we should have stopped earlier, we actually have a little bit more time left. We end up here. And then on the next frame, we'll obviously be moving in the other direction. We'll end up, here. So I've drawn 2 time steps for each example.
Yeah, but for cyan to blue. Sorry.
Yeah.
Because you said that on the first time step we do the separation. Yes. And then on the second time step we would apply the green vector. Would you really mean like on one tick we'll separate and do nothing else?
So okay, so on Cyan, what we're doing, we're move, um, and then
Yeah.
separate,
Yeah.
and then
Okay. So you don't mean
new
like
velocity.
you don't mean game tick when you say time step.
So I'll draw the frame numbers here. So
Yeah.
this is
Yes.
what's happening. So this is the crummy way we'll be doing it here.
No, I totally understand that. I just I I got derailed by when you said time step. I thought you meant frame.
I think I did. I was probably kind of just fudging the terminology.
No, it just made me think about like if, for example, if like move was one and separate was, or move was one and separate was one, and then um, new vector was two. That's what I thought was going to happen. And if that was going to happen that way, um, then I'd be like, well, does that mean I have to like store the collision vector and not do it that tick? And why not do it that tick kind of thing? That's all. But it
Hmm.
sounds like I was, I don't know. Time step is a weird term for me
Right.
because I mean, you're not, you mean like almost like step over, like almost like line of code or operation or logical thing.
Right.
Anyway, point is, yeah, I can follow that. I'm still sort of, yeah, that's fine. Let's just do it this way. I'm still wondering how it's possible that the green arrow can be based only on um cyan and applied to blue without having changed as a result of the separation from cyan to blue.
Oh, right. Okay. So
And maybe that's just dumb like gameplay stuff that I'm making it harder for me to understand.
so in this separate step, we this is where we get the blue box,
Yeah,
and then in this set new velocity step, we're getting the velocity vector green that we're going to use in the next frame.
right. Yep.
So this is, and that's how we don't have to store anything about this collision.
Yeah, I know. I'm talking about like why wouldn't the mass of the two overlaps like cause something different for green? Like
The mass of the two
well,
overlaps.
what I mean is like okay.
Okay, hang on. Let me draw another diagram.
Apologies to everybody else who's trying to listen to me.
I'm sure they might have the same question. Um, are you suggesting a difference between this collision and this collision?
No, I don't know what that little collision. No, I'm not. Yeah, I'm actually not thinking at all about the second way anymore. I'm on the
No,
cheap and nasty
this
all
is
the way.
entirely cheap and nasty. So forget that diagram. This
Oh,
is a
okay.
new diagram. So
Okay.
the difference here is
Yes.
this
It's
is smaller.
what I'm trying to wonder about is um say we're the orange square rectangle
Hmm.
and we've overlapped a triangle and we know that the next thing we need to do in this frame is to separate before we apply the green. Um, Now, what it seemed to me that it was in the original diagram was that the green vector was derived from, in this case, it'd be forget. I don't know what either one is the same to me, but so for the orange one, um, that we decided what the green was going to be based on the orange, um, like based on like the orange square's movement. Like I'm not even looking at the blue one, so just the orange
Yep.
one.
Yep.
Orange penetrates, it's got a motion velocity, it penetrates the triangle, and then we derive from that what the green arrow is going to be. But then what we do, okay, yeah, red arrow is good. Okay, red arrow's the motion, it hits the triangle, and then we like pretend we're not going to separate at all.
Yep.
we're just going to do the crappy one that like eventually it'll move out of the shape. So if that's the case, um, what I thought you were saying was that once we calculate the green arrow based on the orange rectangle, that what we would end up doing is then do the separation and then apply the green one, having not considered at all what happens when two objects of mass hit each other. For example, the little orange guy is like has maybe it's lighter than the triangle. And
Right.
let's just say they have a little
Yep.
higher and lower mass. Now, obviously you could without thinking about separation, the green arrow will have math that reflects the difference in mass, obviously. But what I'm talking about is, wouldn't the separation itself affect the green arrow? Like the fact that we already displaced ourselves in some in the minimum distance, we've already applied the minimum separation, we've pushed ourselves out of the object. That was an instantaneous force. Like we were there and now we're not. Wouldn't we need to kind of like decelerate a little bit, or like cut some off the top? Is there some kind of math for like the impact?
Yes, there is.
Okay, sorry, that took way too long.
No. Like it's an excellent question. You've actually jumped. You've jumped way ahead. And I was just checking whether we would actually do this, and because the maths is more complicated, I actually want to avoid actually doing this yet. But I'll tell you what this is. So this is what's known as an inelastic collision, and it's actually got nothing to do with the amount of penetration. So the fact that this is a bigger vector than this has no bearing on
cool
on that. So these two steps, separate and then set new velocity. And as we were saying, separate is actually optional if we wanted to be really lazy about it. So we don't need to worry about how much separation we have. But when we set a new velocity, we can do an inelastic collision. And that is basically, you can imagine, I'll just draw the obvious diagram for this. So say we have a ball that's bouncing. Maybe I'll just bring out the Wikipedia page because someone's drawn this diagram already. So this is the diagram for inelastic collision, and so we've got a basketball. It's dropping down. It bounces up, and then on the next bounce, it bounces less and less and less, and so on. So each impact of the ball is inelastic, meaning the energy dissipates at each bounce. So that's basically what this means. It's like each time an object hits another object, and this goes into the nitty gritty detail, but it generates a little bit of heat, a little bit of sound, some vibration, and so on. And so it loses some of that energy, and so the collision loses some energy. So you might remember. Sorry?
This is just like when you applied that cheap damping force last time.
Yes.
It's
Let me see if I can pull it. Now this is actually not in the public code base, but let me see if I can find it because I had it a second ago.
I thought we did write it down somewhere at some point.
So this is from the real code. So here, pay attention, everyone. This is the code for weapon, and here's Tritech impact, and this is the 1D inelastic collision response, and you can see we have this restitution factor.
That's where I remembered the word inelastic was from. I remember it precisely from this file because I've seen this file a lot.
Exactly. So the coefficient of restitution, so that's 250. Yeah. So people not familiar with this will remember it's 250 divided by 250. That should be. That's actually 256. So divided by 256. So we've got a 97% coefficient of restitution, So it's very bouncy. So just to draw out that diagram.
So approaching 1 is bouncy, and approaching 0 is sticky.
Yeah. So this is our ball. It's going to fall. It's going to end up here, and it's here's the floor, and it's going to bounce back up again, and then on when it reaches the top after however many frames, it's going to end up here. And so if this is the scale, 1.0 will be there, so there is 0.97, whereas here, if it just stops, that's 0. Basically, that's how that works.
Right. Okay.
And I mean, if you were nuts, you could actually be like, oh look, our coefficient of restitution is like 1.1, and then everything goes wild because your simulation diverges. So yes, you had a question?
I'm just finding I'm thinking about what you said, that like the penetration of the pink things.
Yep.
Yeah, the squiggles. You said it didn't matter, but like triangle could be made out of metal or made out of a bag of water. Like wouldn't that we don't have to consult a triangle to figure that out, because wouldn't it be different?
Well, I mean, I'll just bring up this code because we have this code already. So restitution is the coefficient of restitution. We're just taking the average of the two coefficients of restitution.
Oh. Okay.
This is I can't remember the details exactly. In fact, it looks like, did we just turn off coefficient of restitution entirely and just use a constant? It looks like we did.
Yeah, looks like bounciness plays better though, and
yeah.
We just went with looks like a gameplay decision.
Yeah. So
it's a cartoon though, so that makes sense.
Exactly. So in the physical world, I can't remember the details because obviously I looked at it and I'm like, oh, we could make this more physical. I feel like this should be like because you're actually, I'm not sure you're right, because hitting a bag of water is actually a little bit different because the bag will deform.
Okay, well, I mean like soft rubber versus metal, I guess, or
so taking basically.
Well, that will deform too.
From what I remember, what I remember is, well, the bag of water will it won't spring back into place.
Right, because all the energy is being diffused into the bag and warping the bag, as opposed to it's not coming back out.
So I can't remember the exact details, but taking an average, or however you calculate this, is actually not a physical calculation. This is just a guesstimate, and I'd probably just have to read the Wikipedia article again, which I think I closed.
Right, but I did see you also scaling those by mass and consulting the mass of the other object. So
yes.
That answers my question. We are going to look at the other thing. It's not like it doesn't. You're just saying the amount of penetration doesn't matter, but we are going to look at the material that we're overlapping with to figure out
yes.
The rest.
So I mean, yeah, we've jumped ahead a bit, which is fine. Jumping is good. But yeah, so we've got the mass. So we have these are the factors coming into this calculation here. So we've got the coefficient of restitution, which we could, average out between the two objects, their individual ones. We've got the mass of the two objects, and we've got the velocities of the two objects.
That's the second time that I thought it would be more complicated, and that it ends up just being averaging. When you had me think about the how to solve the many circle overlap problem. And I'm like, it can't be this simple, because it's simple, but then it worked out, so that's cool.
Certainly doing it the simple way is
the simple way is simple.
Well, it is simple.
Right, and then there's no end. You can go as complicated as you want when you try to reach accuracy, which is exactly the same thing as calculus, right? The closer you the more the closer you get to the real answer, the more fine-grained it gets.
Yeah, and I mean, you have to remember we're basically making games here. We're not we're not trying to simulate like a particle accelerator or something. So
Right.
let me bring. Here's the Wikipedia page on coefficient of
Right.
restitution, and it looks like
Oh boy.
yeah, coefficient of will rise and then fall based on collision velocity in a more complicated manner. Thanks, Wikipedia. So it looks like literally the coefficient of restitution means exactly what I drew here. So it's actually not so much a physical property of the object, but it's a measured property of what happens here. And so whatever you measure here, depending, whatever these objects are, whatever you measure is the coefficient of restitution between those two objects. So I guess if we were being physically realistic, we'd actually have to, we'd have a table like, wood, metal, and then wood, metal, and be like, all right, here's our table of numbers that we've determined. But obviously no one wants to do that, so you just take an average and call it a day.
Right. Okay.
But yeah, that must be how you do it if you want slightly more accuracy.
All right, that's probably good for derailing completely at this point.
Yeah, derail is good. And then we'd have our bag of water, and then we just set like all of that as like 0 and 0, and so then we can have our bag, and it would be handled nicely.
Right.
Okay, so where were we? We were trying to. Okay, so we're going to ignore the elasticity of this collision. So we're going to assume it's 1.0 for the time being. And what we're trying to calculate now is how to get from, frame 1, frame 2, how do we transform that vector based on this collision we have here?
Yeah.
So I'm gonna make a new layer.
I'm just trying to ponder that.
So let me start drawing, and we'll see how far we get. I've reversed my colors here, haven't I? And then we hit this thing. It doesn't really matter where we hit it, because we're only thinking about the response here, not the actual collision. And we end up with a new velocity vector. And so, any thoughts on how we might actually calculate this thing? Like, what do we need?
To get the green arrow.
Yeah.
I need to know the. Well, I'm not 100% sure, but I know that I know some of the things that we have in our bag. We can find a perpendicular.
Mm-hmm.
Now, it wouldn't be close to right, at least if you drew it accurately, but it's like if I knew, for example, the angle of the line that the collision has occurred on,
Mm-hmm.
I could possibly take that and and the red arrow, and well, I could get a perpendicular of that line, and then maybe I know there's something involved with the red arrow, but even if for ignoring it for now, I could just get the perpendicular of that, and that would get me in the ballpark, like it's going off in the right direction. But right at this point, it would be like perfectly yeah, it would be perfectly perpendicular to the triangle, and it can't be, because that would imply, I think, that the circle hit the triangle at its center. Um, and it won't, because there's a distance there. So I would have to maybe take the you know some normalized form of that unit circle thing and figure out how to um, subtract that or add that to the angle. But I don't exactly like it's I don't have that cheat sheet in front of me, and it's been a while, but I know that those are the kind of things we're going to need. I know that we have, I mean, I could look at calculate separation, which probably gives me some clues.
Well,
Oh,
let me draw out what the separation will be. So let's say we've intersected here. We kind of have just a bit, just, whoa, look, oh no, it hit. What are we going to do? We're going to do the separation. So we have, an axis of separation. We have several. In fact, we have this one, and this one. We also have the ones for the circles going to the corners, but I'll just ignore them for now. And so obviously this orange arrow is the same as this green arrow, and what we'll find is like, all right, this is the separation vector that we get out is going to be that.
Wait, sorry, can you say that? Can you go through that again?
Yep. Okay, so I'll just draw it slightly better. Here's our triangle, and we have a circle intersecting. We're going to evaluate all of the possible axes of separation, and we know that it's going to be this one. And so what we end up is like, all right, we've got this axis,
right,
and we project onto that axis, so we end up with that vector here.
Then you just perpendicular that one and you normalize it.
And so yeah, we have a unnormalized vector that represents basically the pink one. So we have the pink vector of unspecified length. So it'll be some length, and if we normalize it, we'll just get length 1. So I'll just say this is length 1.
Right. Yeah, I totally I forgot that all of the work we did for separating axes is evaluating obviously every axis, and therefore we already know all of the sort of perpendicular exits out of the shape that we're overlapping with.
So this has the nice property, like it tells us which surface we hit, and it'll also work if we are actually hitting a corner. We'll get this axis here, and it'll tell us that that's the separating axis. So we'll actually bounce off corners properly as well as surfaces. So that's quite handy.
Right.
And you'll also remember the work we did the other day where we handled the case where it's like, all right, well, we've got this shape and this shape, and our ball is coming in like this. And oh no, we've hit both of them at once. If we take an average, the average of that and that is going to equal that, at least in direction. So we'll actually, bounce in and out quite nicely. So this is where the magic of the separating axis thing comes in.
It's awesome.
So,
right. So I guess back to your original question is, how do we we have to know that we're in that situation, and I don't, this might be totally inefficient, but it's sort of like we could kind of just where we right now we press S to do calculate separation and then and actually just force the separation.
Hmm?
We could just wait, and rather than doing that, we could pull that out of S and always do it, and then always look for the intersection count to be greater than 0. And if it is, then we know we need to prepare a response in
Exactly.
simulation.
So I mean, let's have a look at that code. I mean, we'll actually do this later, but simulation, calculate separation. Okay, so S, we've set up some memory for this. We calculate separation, and then we do a thing.
Right. We will do that thing. We will totally do that later, but we're not going to do that now.
So, well, this thing that we're doing is, this is this step here.
Yeah, that's right.
So all we need to do then is be like, and now change velocity. So that's going to be how we're going to do it. So all we have to do is figure out what code we're going to put in here.
And there's really no way of avoiding doing a calculate separation on every tick or sorry, frame. But
yes.
Right.
So
I mean, how else would you know? I mean, you got to do it. You got to do the
exactly. And so we will do it every frame. And if that was a problem, this calculate separation, the only real issue,
trees or whatever.
Yeah, exactly. The only real issue is this ON squared, and so we'd come up with a way that we don't have to do this every frame, because we do have this thing here. It's like, all right, we've got this really fast calculation that tells us whether they're intersecting and does an early out. So it's already very fast for ON squared, and we just have to maybe even make it faster if we need to.
What did you call that term before? I mean, I just said quad tree, which is just like one way to do it, but there was a term you used for kind of separating the world into pieces and like only checking things in the like relevant spot.
So quad tree, QUA tree, is basically
that's like,
we divide the world up, and then it's like, oh, we've got more shapes in this section, so we'll divide this one up, and then you can see how this forms like a tree. So we've got this node at the top is the pink one. Probably keep the colors. So 1, 2, 3, 4, and then it's like, oh, it's got this node has more stuff in it, and so it's like 1, 2, 3, 4, and then it's like this node has more stuff in it. It's like 1, 2, 3, 4, and so it makes this tree that's a spatial tree. And so we might just have one shape here, and it's like, okay, we've got shape here and shape here and shape here and shape here, and it's like, so there's more density to the tree over here. The other thing that I think I probably mentioned was BSP tree. So that's a God, it's hard to spell things and say them at the same time. Binary space
partition. Yes.
So this
space
is
partition. That's what it was.
This is what Doom was sort of the first game to use this in a serious way, I think. And so you have your triangles and stuff, and it's like, all right, well, I've got a whole bunch of triangles, and I want to divide them up. So I work out sort of, well, this is going to divide the triangles in half. Great. And then maybe I do it. So I'll keep my colors so that this makes more sense. So the first level, I'm going to divide it about here to keep them in half, and then I calculate, all right, well, I want to keep half the triangles in one side and half on the other, so I'm like, all right, that's going to be there, and then maybe I will do like this to divide them up at the next layer. And so this has the nice property that it's a binary tree, not a quad tree, and it's easier to store this sort of thing and search it and walk through it. And so you have that, and then it's like blue, and then green.
Why ever use quad then? I mean, there must be some.
I'm trying to remember what the trade-offs are. I think I don't think you ever would use quad. I think you probably always use binary space partition. Quad tree has the nice benefit of, unless you allow these planes to move around, like, do you let them move? I think a lot of implementations don't. So you've got this, like, this is the fixed size world, and you can calculate without knowing the contents of the quad tree where the dividing planes would be. Whereas a BSP tree, the position of the planes typically moves around based on the contents of the thing. So you can imagine in the case of like a Doom level, the level is static, so you can calculate this once, and then you can do lookups into it very quickly because it's a binary tree. Whereas a quad tree, I think, is a better data structure if these things are like moving around. You don't have to keep moving the partitions around and figuring out where they are and thinking about, like, here's 1, 2, 3, 4, 5, 6, 7. Now I can calculate where my first divisor is. It actually makes that process a bit easier. I think in practice, what you typically would do is, rather than a quad tree, you would just, I'll just draw it over the top, you'd just gridify it. You'd be like, and it's like, all right, tell me everything in this grid coordinate.
Right, or basic, and the basic reasoning is only look for collisions in the grid that your player is in, and then ignore everything else.
Pretty much, like, not quite that. It's basically saying, all right, what can collide? It's like, well, this thing and this thing share a grid coordinate, so there could be a collision here. Whereas, these two things,
oh, sure, yeah,
like they are separated in this case by some grid, and so
right. You're just trying to early out and filter out the pieces that don't match what you're looking at.
Exactly. And
but I mean, but if you're doing in our simulation, if we've got shapes everywhere, like, this doesn't really help us, right? Because we, like, right now the entire world's being drawn, so we kind of have to get there eventually. And we have no hero. Like, we're not, like, everybody's colliding with everybody else. I guess maybe I'm confused about how, like, we might use that in just what we're doing now in a way that makes it more useful. Like, what makes it better than just, ON squared.
Well, drawing is ON.
Yeah.
Our collision detection with no space partitioning is ON squared. BSP tree, what is it? Would that be? I can't remember. I think it's like O log n, which is obviously way better than this.
Oh, I see. So with the BSP, we're like gonna like avoid recalculating ones. Like, I don't. Are you saying that we don't, like, we look at the same objects more than once? Because of the ON squared, because we're literally checking everybody with everybody else.
Yeah, so in ON squared we've got a grid, so like, and we have to check, this, like, 1, 2, 3, 4, 1, 2, 3, 4. So we don't have to check 1 with 1, but we do have to check 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6, 1 with 7, and then we have to check 2 with 3, 4, 5, and you end up with this triangle shape, which, geometrically speaking, it's 1/2 n squared, but for big O notation, is the growth factor is n squared. So that's how you end up with O n squared, because you've got, n times n.
Okay, that makes sense.
Whereas in this case, it's like, just say we had a BSP tree, for example. Maybe it would look like this. Let's even say we've actually got a collision for funsies. And so what would happen is, we'd walk this tree and be like, okay, so the number of, have I done this slide? Maybe it's O n log n to walk it. I think it is. No, it's ON to walk it. So yeah, okay. So we walk the tree and be like, all right, that one. Actually, I can't remember the exact big O for this.
That's
but anyway, we end up at this thing here, which is like this place in the thing. Be like, there's two objects in this section of the tree. We can do a collision on them. Whereas every other one, except for this one, like there's two objects here, so that would be, there's also two there. And then so obviously in then we just do collision detection using our ON squared algorithm in each of the leaves of this tree.
Right.
But obviously our N is now very small. So it's like N equals 2. So it's like, well, when N equals 2, we have exactly one collision. So the actual collision thing is very fast. Now, the downside of this is like, doing this is small. I can't remember. It's O log N something. It's the O here is very small to look up into this tree. However, inserting things into this tree is probably ON squared or more. I can't remember.
That's why you want to use it when you can like pre-compute it. And
Exactly. So this is the trade-off you're making, is like how much does it take to insert and remove things into this data structure versus how much it takes to look up and how much memory it takes. So it's like so
right,
insert.
Yeah, move. It's not free. You gotta
look up. I guess in this case, because we're moving stuff around, it's like insert, remove. Maybe you've got a move operation. That seems unusual. But then you have CPU cost, and so you can imagine like a grid structure uses a whole lot of memory, but insert, remove, and lookup is probably like O1 in many cases for CPU, but it's like O M squared memory, where M is whatever the side, the number of cells on a side.
Right.
So that's sort of the trade-off situation for space partitioning.
That's cool.
So eventually we'll get to this, but this is like way off into the future. If we have more shapes than ON squared, will let us deal with. If we want to drop 100 balls into the simulation, we'll look at that. Anyway, we should wrap up.
Yeah, I think we're pretty good. The only thing is, I mean, if we were going to continue, and this is what we'll think of next time, is just like, I was thinking, do we have, we know we've got the separation stuff, but do we have, I mean, I don't think we have all the information we need in pending separation to get to the next time step in our thing, but we can pull it out probably.
So what I will say,
still some more stack Alex.
What I'll say, just so we can end on a good position, and this was sort of the point of this session, is like, all right, we're gonna draw this out so we can think about how to do it, or certainly the case that you can think about how we're going to do this, and that is, here's the diagram. So we have this sort of axis, I guess, and we know which direction it's facing, so we know that this is coming out of the surface, and similarly we have this situation here, and what happens is our red vector, green vector is going to reflect around this. And so that's what I want you to ponder on for next time, is how we're going to calculate this reflection.
When you say reflection, you mean like you're saying the pink vector? Or...
So
I mean,
reflection around the pink vector. So we're trying to calculate the green vector. So
yeah.
we have the red vector, we have the pink vector, we want the green vector.
Right, of course we have the pink vector because we pulled it from our axis stuff. Yeah, of course.
So
I just don't really quite understand the term reflect in this sense.
Well, this is what you will need to ponder on, and that is given a set of vectors, and I'll even draw them off the same origin. How do you get the green one from the red one and the pink one?
Right.
And we should have all the tools to do that. It's just a matter of thinking about it and working that out. So that's basically homework, is not even necessarily to do that. If you can figure that out, that's great. But certainly think about it. So let me bring up OBS and we'll close the stream. Thanks for watching, everyone, and we'll see you next time.